Imagine truly immersive live streaming, where you can view a performer from any angle in real time. This requires generating high-fidelity 3D human representations on the fly. The challenge? Current methods often create massive amounts of data, making them too slow and too large for practical live streaming. Today, we're diving into PointSplat, a groundbreaking approach that tackles this by creating incredibly compact and efficient 3D human models using Gaussian splatting. Traditional methods for 3D reconstruction often work in a view-centric way. This means they predict 3D information, like Gaussian splats, for each input camera view separately. While this can produce good quality, it leads to a huge problem: redundancy. The same parts of the 3D subject are repeatedly encoded across multiple views, bloating the data and making it computationally expensive to process and transmit, especially as you add more cameras or increase resolution. PointSplat's core breakthrough is shifting from view-centric to human-centric prediction. Instead of predicting 3D representations from each 2D view, it directly infers a single, compact 3D Gaussian representation in 3D space. This means the network learns to understand and model the human subject as a unified 3D entity, drastically reducing redundancy. It focuses its predictions only on the relevant foreground regions, leading to significantly fewer Gaussians and much higher efficiency. Let's walk through how PointSplat achieves this. The pipeline starts by taking multiple calibrated images and masks of a human subject. First, it extracts 3D aware appearance features from these 2D images, incorporating camera array information using something called pluck array embeddings. This gives us a rich description of what the subject looks like from different angles. Next, PointSplat builds a robust 3D geometric understanding. It estimates a coarse geometric proxy of the human using a technique called space carving, which essentially carves away empty space to approximate the subject's shape. Then, it voxelizes this proxy and performs ray casting from each input view. This step is crucial. It prunes redundant internal points and establishes explicit 2D to 3D correspondences, ensuring that only relevant surface points are considered for Gaussian prediction. With both appearance and refined geometry features in hand, PointSplat uses a specialized point image transformer. This transformer is designed to fuse the 2D appearance tokens with the 3D geometry tokens. It employs alternating attention mechanisms to integrate global, pointwise, and image-wise information. Finally, in a single forward pass, this transformer directly predicts all the Gaussian parameters, like position, scale, rotation, color, and opacity, to form the compact 3D Gaussian splatting representation. PointSplat delivers impressive results. It achieves higher rendering quality and efficiency compared to state-of-the-art methods, often using significantly fewer Gaussians. For instance, it can achieve comparable or better visual fidelity with a fraction of the Gaussians, like 71,000 compared to over 200,000 for other methods. This compactness is key for real-time applications. It also shows strong robustness to varying input view counts and image resolutions, making it highly practical for diverse scenarios. While PointSplat marks a significant step forward, it does have limitations. The current method may struggle with unbounded scenes due to memory constraints. Also, extending it to create temporally consistent and compact 4D representations for dynamic scenes over time remains an open challenge. Future work will focus on more memory-efficient architectures and exploring advanced 3D and 4D representations to overcome these hurdles, pushing towards even more realistic and interactive immersive experiences.